We're in want of a new idea about how to explain what matter does at the center of a black hole. We're in need of a new law of physics.
Einstein himself concluded black holes were too strange to be real.
Albert never really liked the idea of black holes. He thought they were anathema. This was something that nature should avoid. The places where space and time became infinitely twisted up, he thought, no, nature shouldn't allow that.
Black holes are certainly odd beasts in the universe. They were thought to be peculiar, so peculiar as to perhaps not even really exist in the real world. Simply because your equations show that they can exist doesn't require that the real universe has them.
But over the years, suspicions rose. Stars were found behaving strangely, orbiting invisible objects, moving faster than expected.
Even though a black hole emits no light, is completely invisible, we know exactly what effect a black hole is going to have on its environment, on the stars in its vicinity, on the gas that wanders a little too close. So, will we ever see a black hole? No. But that's not what's important here. What's important here is we can see its paw print.
Suspicious that an enormous black hole was dominating the center of the Milky Way, Eric Becklin was eager to find its paw print. But even with infrared technology, when Becklin pointed the most powerful telescopes on Earth at his target, all he saw was this, just a blur.
The biggest obstacle that we had was the turbulence in our own Earth's atmosphere was blurring the images.
Even when the sky is clear, the gases in Earth's atmosphere are always on the move, distorting distant objects. To bring his view of the galactic center into focus, Becklin would need help. So he appealed to Andrea Ghez, an expert in dealing with the atmospheric blur.
The problems of the Earth's atmosphere is very much like the problem of looking for a penny at the bottom of a river that's moving, where the water is moving by very quickly. That motion of the water distorts your image of the penny. Just like the motion of the air in our atmosphere distorts our images of astronomical objects.
Ghez agreed to take on the quest, to search for signs of a black hole at the center of the Milky Way.
A decade ago, you couldn't look at the center of our galaxy with high resolution, so you couldn't distinguish stars from one another.
Ghez was able to correct the blurring effects of the atmosphere with a revolutionary new technology called adaptive optics.
So this little animation shows you the benefit of adaptive optics. You see the stars without adaptive optics, you turn the adaptive optics on, and all of a sudden you see stars. And in particular, you see stars near the center of the galaxy. Without adaptive optics, you would only see one big blob. And those stars are in fact the most important for us to track. We track all of them, but these are the ones that are the key to the problem. I mean, it doesn't hurt to take more.
Thanks to the new technology, the team could peer into the heart of the Milky Way with amazing precision.
Our view to the center of the galaxy is absolutely superb, and our ability to position stars at the center of the galaxy is like somebody in Los Angeles seeing somebody in New York be able to move their finger like this, okay, just 2 centimeters. That's the precision with which we can measure something that is 26,000 light years away from us.
Once the view was clear, Ghez could start the hunt. If there were a black hole at the center of the galaxy, its paw print would be found in the rapid orbits of nearby stars.
Keep our fingers crossed.
The conclusive experiment to be done that really demonstrated that it was a black hole was to follow the orbits of individual stars in the galactic center very, very accurately and with the highest precision possible.
When an object like a star approaches another, more massive object, the pull of gravity will make the star speed up. If it's orbiting close to a massive black hole, the star should accelerate to enormous speed and then whip around the black hole like a slingshot.
Okay, so we have the black hole here. The more massive it is, the more pull there is. The more pull there is, as it gets close to the black hole, the faster it goes. And we are measuring the speed of these stars. That's the key to getting the masses, measuring the speed of those stars.
This is our roadmap, and that's the center of our galaxy. There's a large cluster of stars that are orbiting the center of our galaxy, and by measuring the motion of stars, and in particular their orbits, we can figure out whether or not there's a central black hole. That environment in there, it's a crowded party.
Gez set out to monitor the partygoers, to track every movement of the central stars.
Basically, the way this experiment works is you take an image, you see where all the stars are, and then you come back sometime later and you take another image and you look to see if they've moved. And so the second time we took an image, we knew we were golden. Those stars had clearly moved.
This one moved to here, this one moved to here, this one moved to here, and so on.
As Gez continued to track the stars, she found some making dramatic hairpin turns.
It made a huge jump to over here. So it went whoop, all the way around. And it's moving on order 10 million miles per hour. So it's just speeding away.
Other astronomers clocked the stars with similar results. Not only were the stars accelerating to phenomenal speeds, their orbits were perfectly smooth. Gez knew that they had to be circling a single massive object. Most black holes are thought to be about 10 times more massive than our sun. But the object at the center of the Milky Way was roughly 3 million times as massive. For Gez and Becklin, that could mean only one thing.
All other physical explanations of what was at the very center were gone. The only thing left was a black hole.
Not only was this black hole supermassive, it was millions of miles wide. Astronomers around the world admitted the evidence was impressive.
I have to say, when I first saw Andrea's video, I was stunned when I saw that star come out of the left side of the frame and go zipping around and go shooting off into the other end of the frame, and it moved around a point in space and nothing was there.
That we could, with our instruments, effectively travel to the center of the galaxy 26,000 light years away and collect the evidence for such an incredible object was really an amazing achievement.
It seemed undeniable, a giant black hole, and at the center of our Milky Way. But how could such a monstrosity come to be? One idea is that black holes are born out of the death throes of enormous stars. Like a red supergiant, a star 10 times more massive than our own sun. Deep inside, temperatures soar above 1 billion degrees. Helium and carbon fuse into heavier elements: oxygen, silicon, sulfur. Eventually, the nuclear reaction creates iron, and the core stops burning. Then, the star implodes under its own immense gravity and goes supernova. What's left is a heavy core of subatomic particles, a neutron star. Only about 10 miles across, but of incredible density.
In fact, it's so dense that a teaspoonful of neutron star matter would weigh about 1 billion tons.
If the neutron star is heavy enough, 3 times more massive than our sun or more, the implosion will continue.
Eventually, the gravitational pressure will be so large that the neutrons themselves will be crushed, and there'll be nothing left to stop the collapse.
Many researchers believe that the Milky Way is littered with small black holes, the dark, dense remains of dead stars.
There must be millions and millions of black holes zipping around our galaxy as we speak. But we don't see them in general because they're dead. They're corpses, and there's nothing there to light them up.
They might be invisible, but to a visitor, these small black holes, maybe 10 miles in diameter, would be especially deadly.
One of the scenarios that always gets me thinking is death by black hole.
Approaching a black hole, the gravity is so strong and space is so warped, it distorts the light all around it. If it's a small black hole, then soon you'll be distorted too, by tremendous tidal forces of gravity.
The tidal force is the difference between the gravity at your head and your feet. The gravity at your feet, if they're closer to the black hole, is a little bit stronger than the gravity at your head, and you feel that as something that is tearing you apart.
Stretching you from head to toe. The tidal forces unrelentingly getting stronger as they exceed the molecular forces that bind your flesh, as you snap into two pieces, and those two pieces snap into another two pieces.
And ultimately, it will pull your atoms apart. You will be, as we say, spaghettified.
And so you end up moving through space-time like toothpaste through a tube. And if I pick a way to go, that's how I'd want to go. It's got to be better than just getting buried. I mean, come on now.